Welcome back. This is video 3 for AP Physics C review, and we're just looking at special cases here. In this case, we have a hanging rope, and we are going to take the end of this rope and slowly move it all the way up to the very top here. And we want to calculate the total work done to make that happen. Well, before we get started on that, let's remember that lambda, which is linear density, would be equal m over L. So there's a total mass of this rope divided by its total length would of course be equal to its linear density lambda. Okay, let's consider a case here. So I am taking the end of the rope and holding it up. I'm going a distance h. Okay, but what length of rope have I indeed made go up? Well, it's going to be h divided by 2. So if you look at this, the length of the rope here is the whole h here divided by 2. So what force is acting on that? Well, the force would be h over 2 multiplied by the linear density m over L, okay, times g. In that case, I'm just using force of gravity. This would be the total mass of the rope I've lifted up and multiplied by g. So therefore, my force is mgh over 2L. Now, remember what work is. The differential expression for work is dW equals d times force times distance. Now, of course, we have a multivariable situation here, but I can substitute in for force mgh over 2L, okay, and I'll substitute in for d. I'll put h in for that. So I don't have a multivariate calculus situation here at all because I've written everything in terms of h. This is the substitution method. So what would that be? Well, dW then equals mgh over 2L times dh. So instead of h, I'm going up a slow amount here. So h becomes a dh. Okay, so there we go. Now I'm going to integrate the left side of dw from 0 to w, and then the right side from 0 all the way up to L. Okay, why? Because I'm going a total length L all the way up to here. Okay, so what am I going to do with that? Well, the integral of that is going to be w for this side, and of course 1/2 h squared on this side. So putting in my definite integral from 0 to L in 1/2 h squared, I'm going to end up with 1/4, because I already have a 2 on the bottom here, and that'll be mg over L times L squared. Okay, and of course I can cancel out one of my L's here, and I'm left with work equals 1/4 mgl. Okay, now let's consider what that means. Okay, if I bring this all the way up to the top here, okay, haven't I just done gravitational potential energy? Of course, that's what I've done. Okay, but how high has my center of gravity actually gone up? Well, if I go all the way up to here, okay, my center of gravity is going to be about right here at the very bottom of it, if you can imagine what that would look like. So I'll have like a little circle like this, or a little loop, I should say. But my center of gravity is only going to be here, which is going to be 1/4 of L. So consider this a differential expression, or you can just say, well, I can use potential energy, because that's what force or work I should be doing. But the center of gravity has only gone up 1/4 of the L. So hopefully that made good sense. Another example here. What if I have a spring and I'm pulling this to the right? And I guess it doesn't matter which way. I could compress it to the left or pull it to the right. I want to find out the total work done if I pull this to a distance x. Okay, well, look at our differential expression. dw equals df times x. Okay, so that looks like a multivariable expression, of course. But we can remember that the force of a spring does equal kx. Now there is a minus sign in there, but I'm not going to worry about the minus right now. So my differential expression, dw equals kx, because I'm substituting kx for force, times dx. And again, my x becomes a differential as I pull it infinitesimally to the right. And one more time, I see that I've avoided the multivariate calculus situation by substituting in a kx for force. Now I can quickly integrate both sides. The left side is integral of dw from 0 to w, and the right side from 0 to x of kx dx. Okay, now we know the integral of x is 1/2 x squared. Okay, and then I'm going to integrate that from 0 to x, so w equals 1/2 kx squared. Okay, now again, we can think about this just like in the other example. All I'm doing when I'm pulling this to the right is I'm causing us to store energy as elastic potential energy. And this, of course, is the equation for elastic potential energy.